Hello, my name is Anurag Nigam, and what I'm going to do is I'm going to start a new series of short lectures or tutorials on digital circuit design using advanced design system. And for this purpose, we are going to use two process design kits. One is a 130 nanometer Cmos process, and the other one is a 7 nanometer FinFET process. The whole goal is to be able to demonstrate circuits to students and explain the internal workings of these circuits using advanced design system. So let's get started. Okay, so I'm going to use this base presentation for explaining some concepts. I'm going to use this scratchpad for writing to explain in between some of the basic concepts, and I'm going to use advanced design system uh, which I'm going to launch right now from the start menu. You can just click this to launch the advanced design system from Keysight. So meanwhile, if this software launches, let me just cover some basics. So you can dismiss this screen by pressing escape. Okay, so digital circuits. Now these are the circuits which have signals which may be voltage or current, which take values from a finite set. Now this finite set is usually a two-member set, which is 0 or 1. Now in physically the circuits, these 0 is represented by ground and 1 is represented by VDD. Now what can happen is you can also reverse it. Now there can be circuits which can be between minus VDD and plus VDD, but anyways there are going to be only two possible states, and one would be mapped to 0, other two possible values, one will be mapped to 0, other will be mapped to 1. So now the question comes is, such a circuit is called binary circuit, but the question is why would I use a circuit which has only two voltage values? The reason is very simple. Now these two values, they are far apart, so they are the highest voltage and the lowest voltage, right? Now as they are far apart, if there is a noise in the system which basically disturbs the signal values, then they are so far apart that the noise is not going to disturb your circuit response or disturb your the value of the signal, right? So it has a very high noise immunity. So the reason we go for binary circuits is very high noise immunity, and this is because we have only two values. We have to judge between only two values, right? And these two values are the farthest values apart, right? So that's the reason for doing binary circuits. Now in circuits we can have more than one value. So the set need not be just a binary set. It can be more than one values, but such circuits such circuits are much more complex, while the binary circuit is simple, because the circuits can be minimized using what is called binary algebra, right? So that's the reason why, or Boolean algebra, right? That's the reason why we are going to design binary circuits. Now coming to classification of these digital circuits, the circuits can be classified as combinational circuits, sequential circuits, and state machines. Now what are combinational circuits? The circuits which do not have a sense of passing time. Now a circuit can have a sense of passing time when it has a memory element, when it can store the previous states. Now in a combinational circuits, the output is a function of all the inputs, and it cannot be a function of the output, because this will be a closed loop, right? So in combinational circuits, output is the function of all the inputs at the current time. There is no concept of values at previous time, right? So these are called combinational circuits. These are memoryless circuits. Examples of these circuits are logic gates, multiplexers, demultiplexers, coders, decoders, arithmetic and logic unit, multipliers, barrel shifters, adders, subtractors, parity checkers, error detecting and correcting circuits, right? So these are combinational circuits. Sequential circuits are those circuits that have the sense of passing time. You can have only a sense of passing time when you can store the previous state, or you have a sense of past. For that you need a memory element. The basic memory element is going to be a D flip-flop or a D latch, but then there can be other derivations of D flip-flop. For example, they can be T flip-flop, JK flip-flop, etc. Right. So these sequential circuits, the various examples are a register. A register is basically a single flip-flop which can store 1 bit, or it can be a lot of registers which can store an entire binary word, right? Or it can be the shift registers which are made out of the registers itself, so that you can shift the bits to the left or the right. They can be ring oscillator kind of circuits. Rather, I would say not ring oscillator. You can circulate the bit within a register, right? So such circuits are there. Then you can have these shift registers with feedback. They are usually in the literature as PN sequence generators. Then you can have frequency dividers, sigma delta modulators, digital filters, first in first out and last in first out kind of stacks, and memory registers. And then in a processor, for example, they can be register files, etc. So these are the examples of sequential circuit. Now state machines are a combination of sequential circuits as well as combinational circuits. As the name states, this is a digital circuit which can have a certain state. So there is a state to start with, initial state, and then the circuit can migrate from one state to another depending on certain inputs or depending on certain state variables. So let's say if there are, like, say 4 states in a circuit, then each state can be identified using a unique word, right? So for example, 4 states would require 2 bits. That will be unique identification of the 4 states. So this is an example of finite states in this machine. So it's called a finite state machine. Now when you transition from one state to another based on the inputs or state variables, okay, then this can be classified as a Moore or a Milli machine, depending on whether the input is influencing the shift in the state, or whether input is not influencing, only the state variables are influencing. So we will come to state machines as we go further in the design. Now let us say how the digital circuits are designed in the industry. They are not designed using transistors. They are not even designed using gates. What has happened is for prototyping purposes, there is a reusable hardware which is called FPGA, or Field Programmable Gate Array, and similarly there is another programmable hardware called CPLD, or Complex Programming Logical Device, right? So these two reprogrammable hardwares are usually used for designing circuits for prototyping, and you can configure this reusable hardware using a hardware description language. Some of the examples of hardware description language are Verilog, VHDL, System C, and then you can also use C for doing this, but most commonly used are Verilog and VHDL. So this is one flow, okay? This is one flow of designing, okay, where the target design is a programmable hardware. So what you see here, design and synthesis, there are 2 flows. One is the HDL based flow, in which you write the code or describe a digital circuit using a hardware description language, or HDL. Or you can also do something called high level synthesis, where you use a high level language like C or C++ or System C, right? You can, after describing the circuit, you have a software tool which automates a generation of a bit file. And what these programmable hardwares are, these are usually lookup tables. So in FPGA, for example, there are no gates actually. There are lookup tables, and these lookup tables are stored in registers. And then there is a memory element like flip-flop, and then there are multiplexers and demultiplexers to design any combinational circuit. So these 3 elements are used to make what is called programmable logic, or it's also called CLB. It will be a what you call logical block, which can be used to implement a functionality. A number of logical blocks are provided in FPGA, which are basically connected using a switching matrix. So you can use these CLBs. Okay, you can use this CLBs to design much more complex circuits by just configuring the switching matrix, right? So this is what you call FPGA. Okay, similar to FPGA, there is something called Cpld, which I'll not go into details because this is not very much used. The advantage of Cpld is high configuration speed. Actually, what happens is as soon as you turn a FPGA on, you need to take the bit file and configure all the switches in switching matrix. This usually takes time. Now in Cpld, this logic is built into each cell, right? So Cpld basically boots up faster, but because of the migrating to lower gate lengths, the device is becoming faster and faster, and FPGAs are as fast as Cplds these days. And so Cplds is basically going down in the race compared to FPGA for programmable hardware. Now besides that, there are something called SoCs. Now what these SoCs are, you have a programmable hardware called FPGA. Along with it, you put in a processor, which is basically a fixed hardware, right? So you can have a programming logic in the fixed hardware like FPGA with this memory, with its what you call memory cells, and your you can save the entire program there and run it. Now this programming logic is going to control a configurable digital hardware, right? So this solution constitutes a complete digital solution, and you do not require what you call a design of digital circuits on the board, right? So FPGA basically provides a programmable hardware, and there is a fixed component to it, which is a microprocessor, which is a controlling unit, right? So this is what happens in case of FPGA. Let's look at the other design flow. In the other design flow, we have got a schematic based entry. Now in this schematic based entry, we are going to use transistors to design circuits. The first thing which we are going to design is logic gates, and then we are going to, using those logic gates, we can design what is called flip-flops, and using flip-flops we can design much more complex circuits. Now a schematic based entry is not preferred these days, because if there are large circuits, right, these large circuits are easy to define using a language, and they are easy to communicate, while schematic based entry is for smaller size circuits, but they are very good for understanding the concepts of operation of a digital hardware, right? So we are going to start with a schematic based entry, and later in the series we are going to shift to HDL based design or synthesis on FPGAs. Now the end device or the target device for schematic based entry is a application specific IC. Now this process of generating application specific IC is also heavily automated, but this is not as heavily automated as the other flow. In the other flow, once we have a FPGA, we can turn this into a ASIC, and there is a standard procedure to do that, right? So this is mostly done by the companies who provide FPGA, and it's a time bound process, and it's already optimized flow, so it takes less time to go from FPGA to ASIC. So people usually take the second HDL route rather than the schematic entry route. Okay, so now what are the various activities in designing a digital circuit? One is you define the logic using a Boolean expression, for example, or you define the logic using algorithmic chart, or let's say you define the functionality of a digital circuit just by English description, right? So once you have that, you can basically put together a circuit using gates, or you can put together circuit using just the storing elements like registers, and you can specify how the transaction takes place between registers. This is referred to as register transfer logic, or RTL. So we can define a digital circuit using gates, or we can do it using a description which is a register based transaction, which is called RTL. Now once we have designed that, what do? We want to minimize its cost. So what is the cost of a digital circuit? The cost of a digital circuit is the number of gates and the number of inputs to those gates, and this does not include NOT gate, right? So if you do that, that will be the cost of the circuit, and the goal of minimization is to minimize the cost of the digital circuit. Now once you have done a minimized circuit and you have put down a circuit, first thing to check is functional coverage. Now for all the possible input set, the possible output set is defined. So if the entire input output set is covered, that will be called functional coverage. The next thing is up to what frequency this can be operated. So what can be the maximum clock frequency? Now that depends on the various critical paths between input and output, which are the worst delay cases, right? So that will basically decide what is the highest operating frequency. Now this is called time enclosure, and when we look at the signals, when they propagate between input and output, they go through degradation, right? So that basically is referred to as signal integrity. So we design for a certain signal integrity, right? Now we can tolerate certain errors, so that's basically a limiting factor on signal integrity. Now besides that, there are some other factors which you have to consider. For example, what is the power consumption of the circuit while it is in operation, also when it is in standby. So power management is another activity which we have to carry out. The last thing is, once you have designed a ASIC, it has to be packaged in a package, and package also has influence on the performance of the ASIC. So we have to look into the package design for digital hardware. Now what tools do we have in hand? Well, when you go at a very small level, we have got what is called Karnaugh maps or K maps for minimization. We have got Quinn-McCluskey's table method for minimization. We can use Venn diagrams for minimization, and then we should also know a little bit of graph theory and automata theory for various circuits, right? Now in case of finite state machines, we work with state diagrams, state transition tables, and stuff like that. In case of asynchronous circuits, we deal with something which is called Parity net or INETs, and asynchronous circuit design is based on handshaking, and there is no clock, and so that's why it is called asynchronous circuit. It is based on basically the flagging, like so there is no clock involved. So there, to solve the logic, you have to represent a circuit as a Parity net or a INET. So these tools are there. Besides that, in terms of software, we have got tools for doing parasitic extraction. So once you have done a circuit, for example, so all the components in the circuits are usually transistors. Very rarely we use resistors in digital circuit, right? So in this case, the various parasitics of a transistor, right, they can be extracted by mathematical extraction, or they can be extracted through a EM simulation, which is a full field solution, right? So usually if the circuits are large, we do not go for EM simulation, we go for some form of a mathematical extraction of parasitics, right? So there are lots of tools for doing this extraction and back annotation, and then we can again do the timing closure, because parasitics capacitances decide the delay, right? And the resistances decide the delay. So because of that, we have to do the timing closure along with the parasitics. So this is done using these extraction tools. Besides that, we may need to do thermal simulations, because transistors have certain safe operating temperatures, right? So when the circuit dissipation is very large, the die gets heated up, right? So the transistor junction temperature rises, and we have to devise a thermal solution to take the heat out of the die and spread it out so that it can be dissipated out, right? So this thermal design becomes important when the power consumption of a digital circuit goes up. and there are different EDA tools for even figuring out the power distribution across the chip. For example, from ANSYS they have got IcePack and things like that, right? So there are lots of software tools available to us to do digital circuit design, and we know what are the various activities in a digital circuit design. Now let's go to the next slide. Now a circuit design can be automated, and it can also, there are lots of advantages of automating a circuit design. Now this basically is based on extraction level. So for example, if I was to take a complex circuit and start designing using transistors, this approach will be very complex and difficult and very time consuming, involving, because I'm starting from scratch from transistor, which is the lowest level of abstraction. The next higher level of abstraction is I can use gates rather than transistor to represent a logic. So we can work in terms of logic gates, right? Then that's there's another level of abstraction where we can work in terms of circuits. So for example, if you look at structural design here in this chart is called Gajeski's Y chart, right? So there are different ways of representing a design. It can be a behavioral representation of a design, it can be a structural representation of a design, it can be a physical representation of a design. So in the structural representation of design, the lowest level of abstraction is transistors and traces connecting them. Then the next higher level of abstraction is gates, latches and flip-flops, right? So these are the basic circuit elements which can be used to design combinational sequential circuits and state machines. A still higher level of abstraction would be if I have a functional blocks, for example arithmetic logic unit, registers and memories, and using these blocks I can make mega blocks, right, which are even higher in hierarchy, and use those mega blocks and connect them to make a system. So you can have mega blocks, then you can have macro blocks and IOs. So this would be where you would be directly using some form of a intellectual property or IP from some company, where you can just integrate, for example let's say a bus architecture on ARM processor. So that is a XC. So we can directly use their buses in the digital circuit design, right? So that would be basically a macro block and IO level what you call abstraction. So this is the hierarchy in the structural design. In behavioral design, okay, we can start with the transfer function, we can have truth tables and state graphs, we can have transitions and operations between states, right? And then we can design tasks, and then using various tasks we can design algorithms, and this description basically is automated to generate the circuits, and this is usually the route taken by what is called the high level synthesis. At the high level we can just specify the algorithms and translate that into a digital circuit. So that will be a behavioral level description, right? So now let's say we have physical design. In physical design we usually do not work manually with physical design. In small circuits you can do that, but when the transistor count becomes very large, the transistor layout, which is basically just a bunch of polygons on different metal layers for connecting different devices, right? So these are different mask layers, right? So these mask layers have these polygons and these are connected together, so that constitutes a component, right? So these different components are connected to make what is called standard cells, and these standard cells are well tested and optimized over a period of time, and then you have a library of these standard cells. So what happens is, let's say I have described a circuit as a HDL or hardware description language, and then I would have an algorithm to map this HDL to a standard cells. So that way I can directly target a ASIC instead of FPGA coming as an intermediate step, right? So this form of development would be called design using standard cells. This is what we are going to do in this series. Then there is a placement and route. This is also automated. If you do it manually, as we do it in RF circuits or let's say analog circuits, then it is going to be very involving because the number of transistors in digital circuits are much higher, right? So again, in that, even if we are doing it, for small circuits, we do what is called floor plan. We decide where which standard cells are going to be located, how they are going to be orientated, and then how they are going to be routed, how they are going to be connected together with traces. This would be coming under floor plan, right? Once you have the IC, you would work on the evaluation board on which this IC is mounted, and then there is going to be interconnection. So for example, a motherboard of a computer, right? So the processor is a IC, right? But then it is connected to memory, it is connected to PCMCIA slot cards, and it is connected to other peripherals using what is called PCI Express, a bus technology on the board which is called PCI Express. So the entire system generation is basically IC, but then this IC is connected to all other ICs on the board, and for that we are using a certain bus architecture like PCI Express, right? So this would be called a physical design, right? So we have got a behavioral description of a design, we have a structural description of a design, or we can have a physical design. So accordingly you can have a various specializations. So one cannot be every designer. Okay, you can have a certain specialization, but in this course I'm going to teach you how to be basically how to have information of all the domains, so that later on you can decide which domain to go to specialize. Now going further, okay, now in this slide what I'm trying to show is everything boils down to, so all the circuits, no matter how complex they are, right, at the very low level of abstraction they are just transistors connected together, and the speed of the circuit basically depends on the parasitics like capacitances and the trace resistances, right? So there are delays involved in any digital design, and this is because of the resistances and the capacitances, right? Now as the device becomes smaller and smaller, these capacitances become smaller and smaller, and then these trace resistances become smaller, the density of the circuit goes on increasing. Now this brings us to a famous law which is called Moore's law. Moore's law states that initially when Gordon Moore, one of the founders of Intel, he had an interesting observation that every 2 years, right, the number of transistors in a circuit would double, right? Later it was the Moore's law was modified to every 1.5 years they would double, and then it went scaling down to a year and things like that. It was called Moore's law, and this Moore's law has continued for almost 40-50 years now, right? So in 1960s it was given, and today is 2020, so it has been there for almost 60 years now, and somehow the technology is upscaling to support Moore's law. So earlier you used to use what is called MOSFETs, and these MOSFETs are the devices, 3-terminal devices, which have got drain and source, and they have got gate, right, which is a controlling element between drain and source. So this gate length is usually called the minimum feature length, is the minimum gate length, right, by which we identify a certain CMOS technology. So this gate length has been progressively reducing. So let's say in 2000s you would see circuits which are like 0.5 micrometer gate lengths. Now later on this kept on reducing, and today we are at a place where we are talking about 2 nanometer kind of gate lengths from TSMC. So what is happening is, in this course I'm going to see a transition from 130 nanometer CMOS to 7 nanometer CMOS, and the maximum clock frequency can go from 8 gigahertz to 50 gigahertz, right? So I have a PDK which basically will help you to see this difference of migration, this difference in circuit designs, and various things like power consumption and all that. Now what I'm showing next is, so this is what we are going to do using standard cells which we will make using transistors, and we will do a standard cell based circuit design. Besides that, there are reusable hardware platform, like for example I'm showing here a FPGA from Xilinx. This is Arctic family. Now there are 3 families in Xilinx FPGA. These are Vertex, Kintek, and Artix. Artix is the the entry level. It's mostly used for small prototyping by students to learn the concept. And this is basically, this flow uses uh, uh, EDA, or what you call uh, automation software for doing this design, that is called Vivado. So Vivado is now called Vitis, right? So we will see, because this Vivado is not only used for FPGA design, but it is also used for SoC designs. So Vitis has got MPSoC support, where it basically divides the functionality between programming logic and the digital hardware logic, right? So digital logic, right? So that is automatically done in Vitis. This is something called design partition, which we'll come to later on when we start designing. What I'm showing here is a 14 nanometer based CMOS based a Zybo board. Now this Zybo board basically is using a zinc SoC, and this zinc SoC 7000 series, right, has got a RTX as a FPGA, and then it has got A9 ARM core, right? Two A9 ARM cores on it. So this constitutes SoC. So we can design something like a programming logic on A9 ARM processor, and then we can do a digital logic using RTX FPGA on the same chip, and the software we are going to use is Vitis, right? So this will be far later in the development. Now let's go ahead and start looking at gates, right? Before even we look at gates, I want to explain you something, right? This is called number system. Okay. Now if a digital circuit takes a value from this finite set, okay, so this will be called a binary number system. If it takes the value from this set 3, 4, 5, 6, 7, 8, 9, right? Now this will be called decimal, right? Now if it takes value from 0 to 9 and then followed by A, B, C, D, E and F, now this will be called hexadecimal. Now if it takes a value from 0 to 7, that will be called octal. Now in case of digital designs, we can represent a binary word by 0B as a prefix followed by the number, so that would be a binary number. Now in case of decimal, we rarely use decimal because this is something which is somewhere between hexadecimal and binary, and so we use something called hexadecimal, and the way you write hexadecimal is 0x and then this hexadecimal. Now octal, you usually proceed with a 0 followed by these numbers, right? Now what happens between binary? So each bit basically represents two states here, two states for each bit. Now in this case hexadecimal, each digit here represents 16 states. Now what are these 16 states? These 16 states are 0 to 9, A, B, C, D, E, F. And what is the relationship between hexadecimal and binary? So if we club 4 bits of binary, that can represent 16 states, so that will be a hexadecimal digit. So for example, let's say I have a number which is 11010101. So now I club these, okay, so this represents 5, okay, and this represents D, so this will be called D5. So the way you will write it as 0x D5, right? So this is how you convert a binary number into hexadecimal. So let's say if I have 32 bits, then how many digits in a hexadecimal? So 32 bits means, so now here if you can see there are 8 bits, you need 2, so basically 4 bits you can represent by one hexadecimal digit. So if there are 32 divided by 4, right? So what will be 4 into 8, so you will have 8 digits over here of hexadecimal. that will be 32 bits. Now octal numbers are rarely used because most of the work is done by the hexadecimal number, but in this octal number we can pair 3 bits. So for example, here I can pair these 3 bits and put a leading 0. So in this case it will be 5, and this one will be 2, and this one will be 3, and I'll put a 0, leading 0. So this will be octal representation of this number. So you understand, this is a hexadecimal representation, this is a octal representation. So this is all about the number system. Let's go back to what are we going to do. Okay, so before that, okay, let me try to explain. Okay, now a digital circuit can be expressed in terms of inputs and outputs. So for example, I can write an expression. Okay, so the expression can be as simple as Q as the output is going to be A B bar plus A bar B. Okay, so now let's try to understand what this representation is. Dot signifies a AND gate, right, and plus signifies a OR gate, and then a bar on the top, it is negation. Okay, so for example, let's look at negation, right? So negation means if there is a input A which is 0, then the output is 1. If the input is 1, then output is 0. So this is called negation. So I can represent this Q is equal to A bar. So this is also called a NOT gate, right? Now then, besides NOT gate, you have got AND gate and OR gate. So what is a AND gate? So for example, I can write this as A B, and I can specify all the states here, right? So if I put 0 0, then the answer is 0 0 1 1 0 1 0 1 0 0 and 1 1 1. So what is an AND gate? AND gate is a gate where both the variables have to be 1 to result in an output of 1, right? So that is an AND gate. Now similarly, there is a OR gate. In case of OR gate, what do you have? Okay, either of the inputs has to be 1 for the output to be 1. Okay, so 0 1 1 1 0 1 and 1 1 1. Okay, so this representation of all possible inputs and the corresponding outputs is known as truth table, right? So this is a truth table for AND gate, and this is a truth table for OR gate, and this would be called a truth table for NOT gate. So these are the basic gates. But are these gates, okay, really good for representing a logic in circuit? So the answer is no. So to represent circuit, represent as what you call a logic, okay, we need a NOT gate. So there is no replacement for a NOT gate, and then we just need a NAND gate. Okay, we don't need any other gate or NAND gate. And another form, we can have a NOT gate, and then we can have a NOR gate. Okay, so these are two philosophies here. I can design entire circuit using just these gates. Now what is the truth table for a NAND gate? Let's see that. So for 2 inputs, okay, the truth table will be like this: 0 0 0 1 1 0 1 1. These are all possible inputs, right? So the NAND gate output, so this NAND gate, the output is low when both inputs are high, otherwise it is high. So this will be high, this will be high, this will be high, this will be low. So this is a truth table for a NAND gate. For NOR gate, it goes like this. Okay, so 0 0 0 1 1 0 1 1. Okay, so the output is going to be high only when both the inputs are low, otherwise it is going to be low. So this is a truth table for NOR gate, right? So using either of this, we can represent circuits. Now there is another way of representing gates. Okay, usually it can be represented by a symbol. So for example, a AND gate for 2 inputs would be like this. So this would be an AND gate. Then OR gate would be represented like this. right? So this will be a OR gate, right? A NOT gate would be represented like this, so this will be a NOT gate, right? So a NAND gate would be a, so if you see the two tables, right, you will see that Q in this case is going to be inversion, right, between AND and NAND. So this will be, NAND will be a NOT following the AND. So that's how I can represent a NAND. So this will be a NAND gate. Okay, then the other thing is you can have a NOR gate. So this will be a NOR gate. Now besides that, there are two more gates. Okay, so these are called parity checkers. So let's try to see what this is. Okay, if you have two inputs A and B, and then you have output, so output is going to be high only when the two bits are dissimilar, or their parity is a odd number. So if there is a odd parity, so for example 0 0, so there is no 1 here, right? So this is the even parity, the output is 0. If it is 0 1, the parity is odd now, right? So when parity is odd, this will be 1 1 0 1. Now if I put 1 1, the parity is even now, right? So parity is basically the number of bits which are 1. So that will be the called the parity. So parity of this input is even, so the output is 0. So this is called a XOR gate. Okay, similarly if you put a NOT gate in front of a XOR gate, it will be called XNOR gate. So let's do this. Okay, so 0 0 0 1 1 0 1 1. So if the parity is even, then it is going to be 1. Okay, so this is 1, this is 0, this is 0, this is 1. This looks like an inversion. So XNOR gate looks like an inversion of a XOR gate, right? So how would I say that? Okay, so now I have to represent them in circuits. So this is how I would represent a XOR gate, and this is how I would represent a XNOR gate, right? And basically what is the relation between them? So this gate is equivalent to a NOT following a XOR gate. So this is also a XNOR gate. Okay, so once we are clear with this representation, now there is another way of representing. This is called Boolean expression. So the first expression which I wrote here, this is a Boolean expression for XOR gate. Let's see how it was done. Okay, so now in this case, if A is 0, okay, so if A is 0, then A dot B bar. Okay, so let's look at A dot B bar. So just pick those which are 1, right? So let's try to represent this one. Okay, so to represent this one, it would be either A dot B bar. Okay, so for this one, this is A dot B bar is going to be 1, and then for this one, A bar dot B equal to be 1. So the net resulting expression would be A dot B bar plus A B bar dot A bar dot B. Sorry. So let's look at eraser. Here is the eraser, and then a pen. Okay. Oh, something else has come up. Okay, here is the pen. Okay, so this is a Boolean expression. Okay, and this is sum of products. So you can see these are product terms. Okay, so these are product terms, and it is sum of these product terms. So that is why it is called sum of products. And this sum of products are usually represented as NAND logic. And we will come to why it is a NAND once we look at the circuit of a NAND gate. Now similarly, I can represent this NOR gate. Okay, so this NOR gate can be product of sums, right? So basically what you can do is this, and then you can do this. So if I simplify this, I have a dot a bar, which will always be 0, right? So this will always be 0, plus ab plus a bar b bar plus b bar b, and this would always be 0. So the result is this. So this can be represented as NOR logic, or product of sum Okay, now why do I have two logics? Okay, usually the NOR gate, okay, is slower than the NAND gate, and this is because the Pmos device is slower than the NMOS device. We will come to this once we represent a circuit for NAND gate and an OR gate. Okay, so what it says is that sometimes when we represent a circuit as a SOP logic, the cost is less, and sometimes when we represent it as a POS logic, then the cost is less. And what is the cost? So for example, if I look at this XOR gate, in XOR gate we have got two NAND gates, so we have got two AND gates, and then I would use one OR gate, right? And then there is a what is called the inversion or NOT gate. I will not count the NOT gate. So now this has got two NAND gates, will be having 4 inputs. Each one is having 2, right? So two NAND gates are going to have 4 inputs. One XOR gate is going to have 2 inputs, and I can ignore the NOT gate. So what do I have? I have got 3 gates here plus 6 inputs. The total cost of the circuit is 9. Okay, so the 9 is the cost of the circuit. Okay, the idea is to minimize the cost of the circuit, and we will come to why we minimize the cost of the circuit. Because see, what we want to do is minimize the number of transistors, so that will be minimizing the gates, and then we are going to minimize the inputs, right? So this has to do with something called fan out or timing, right? So this we will come to later on. So usually it is the power and the delay. So the power term comes from how many gates do I have, and the delay comes from how many inputs do I have. So that's the cost of the circuit, the number of gates and the number of inputs. So that's the cost of the circuit. So with this background, I think we are ready to start, right? Before this, I'm going to explain you one more concept. Okay, there are different logic families. So for example, there's something called static logic. Now what is a static logic, right? If the output, okay, let's say output Q is connected to either of supply rails. Okay, now what is a supply rail? Okay, that is basically VDD and ground. So VDD is one end of the one supply rail and ground is another, right? So these are called supply rails, right? So this supply rails, right? So now the thing is, if Q is connected to either VDD or ground, okay, that form of logic would be called static. Okay, now if Q is connected to input in some way, right? Input not in the sense of so there is a connection between output and input, so that will be called transmission gates. Okay, so we have got logic family like static logic, and then you have got transmission gates, right? So we are going to first explore these, and then there are others, pass transistor logic. So basically that's one of the transistors is removed from transmission gate, like PMOS transistor, because it's slow, and we have only NMOS pass transistors. This will be called pass transistor logic, or PTL, right? So then what happens is you will need a output pull-up circuit. Okay, so that will be PTL logic. So we'll come to these once we start exploring these gates, and I'm going to only explore those gates which we are going to use in the design. There are different logic families which are available, which have been explored, right? Like for example NMOS only, right, which will be there will be only NMOS devices and the pull-up resistors. So I'm not going to go into the logic families which are kind of obsolete. Then there is something also like ratioed circuits, where the pull-up device basically is always on, and then the output becomes 0 only because the NMOS device pulls it down. So these are called ratioed circuits. So then pull down depends on the ratio of Pmos size to NMOS size. So I'm not going to cover these ratioed circuits and all that stuff because these are kind of obsolete. Mostly in CMOS we stick to either this or to that. So I'm going to cover this. Okay, so let's go ahead. So I am going to put this aside. Okay, so I am going to just discuss basic gates. Okay, and I'm going to start with the static logic. Now there is a very simple way of defining static logic family, right? So static logic. Okay, so how do you design circuits? Now you should remember only two things. One, a Pmos device is represented like this. In this case, this is the source, this is the gate, and this is the drain. Usually the source is always at the known potential, and in case of Pmos devices, source is always at a higher potential than gate and drain. That's why this is always connected to supply, VDD. Okay, and then there's another transistor. Okay, in this case it is drawn like this, right? And this is source, this is gate, and this is drain. Now in this case, source is always at known potential and it is always lower than the gate and drain potential. So this is usually connected to ground. Okay, so now if you see, now this is also called, so this is a Pmos device and this is an NMOS device, and these are how they are supposed to be connected. Source is always at a higher potential than gate and drain. That's how a Pmos is connected, and source is usually identified. So sorry about that. Source is usually identified with this arrow. So wherever this branch has an arrow, that means that's the source. Okay, so in this case, source is always connected to a lower potential than the gate and drain. So that's a NMOS. Okay, so now this, if this is the output, for example, so then this will be called a pull-up device, right? And in this case, if this is the output, then this is going to be called a pull-down device. Okay, now one more thing to notice is pull-up device is active low, which means that if gate voltage is lower than the drain voltage, then only this connection will be there between source and drain. So pull-up is an active low switch. Okay, so this is an active low switch, and NMOS is an active high switch. Active high switch. So what do you mean by active high switch? Active high switch is the drain and source are connected together when the input is high. So this device, Pmos device is on when the input is low, and NMOS device is on when the input is high, and the Pmos device is going to transmit a VDD to the output. So basically Pmos device transmits 1. Okay, and NMOS device transmits 0. Okay, so this you should remember. Pmos device transmits a 1 and NMOS device transmits a 0. Pmos device is active low switch, NMOS device is an active high switch. What it means is Pmos device is turned on when the gate input is lower than the source input, and so source and drain would be connected together. To turn on the NMOS device, the source and drain would be connected together. To turn this on, the gate has to be high, so that's why it is an active high switch. So once this is out of the way, then we can look at how to implement the circuit. So for example, let's say I want to implement Q is equal to A bar. Now we think like this: if this expression was 1, so I am constructing a pull-up circuit, and then if I say this expression is 0, I am constructing a pull-down circuit. Okay, so the convention is very simple. Okay, what input would result in 1? Okay, so in this case, okay, if I give a as a low input, it will result in q, which is high output, as 1, right? So basically I just need one device as a pull-up device. If a is low, so basically if a is low, then the output is going to be 1. So this is how I constructed a pull-up device. Now let's construct it a pull down device. So there is no logic actually here, there is only one variable. So if a is high, then the q would be connected to ground, so that will result in 0, right? So first I constructed a pull-up circuit by equating it to 1, and then I constructed a pull-down circuit by equating it to 0, right? So the net circuit would be pull-up plus pull-down put together. Now if there is a bar on the entire expression, then the inputs are going to be same, but if there is no bar, then the inputs are going to be inverted. So for example, there is a bar here, right? So this input would be a and this input would be a, and then they can be connected together as just this. Okay, so this would be a and this will be q, and this is VDD and this is ground. So this is a circuit for NOT gate. Let's try to construct an AND gate. So q is equal to a b, okay, or rather a NAND gate. Okay, so this is a NAND gate, right? So forget about the bar, just think like that. If I want to implement a 1, so this would be 1 when either a is 1 or b is 1. So there is a either case, sorry, this will be 1, right? So when either of them is 0, right? So either a is 0 or b is 0, this is going to be 1. So it's a either case. So either means that the switch which I'm going to use for pull up, so these are the two switches, right? And this is my output. So either means that these two switches are in parallel. Okay, okay, so either a should be 0 or b should be 0 or both should be 0. So if it's a either case, then the two transistors, pull-up transistors, are in parallel, right? And then if I equate it to 0, so it is 0 when both are 1. So both case will be in series. So pull down circuit will be two switches in series. So I constructed a pull-up circuit here and I constructed a pull down circuit here. Okay, the either case results in two transistors in parallel, and so that is how a pull-up circuit was constructed. And you are going to use Pmos devices, right? Now in case of 0 output, you need both of them to be 1, so it's a both case. Then two switches are going to be in series, and now to control them, right? So let's replace this with devices. Okay, so one device for a, one device for b. So this would be like this, and then there will be two pull down devices which will be in series like this, right? So this is q, so this is equivalent to that, right? So now the question is, what this is the circuit we got. Now is there a bar on the expression? Yes, there is a bar. So which means that the inputs can be connected as is, a b a b. You are done. So this is a NAND gate representation. Now let's look at a NOR gate. A NOR gate would be represented like this. Now to construct a pull-up circuit, equate it to 1. Now this is going to be 1 when both are going to be 0. So both means they are in series. So two switches are going to be in series, right? So this will be the output. To construct a pull down circuit, equate it to 0. Now it means that if either of the inputs is high, right, then the output is going to be 0. So this is either case. So now it is going to basically be in parallel. So this is either case. Okay, so now this can be represented in transistors as two PMOSes in series, because this is a both case, and then two NMOSes in parallel, because this is a either case, right? So, and this is the output. Now question is there a bar on the overall expression? Yes, there is. So I can just put here a, b, a and b. We are done. Now, so this is a NOR gate. So this is a NAND gate, and this is going to be a NOR gate, right? Okay, just 1 second. Okay, so this is a NAND gate and this is a NOR gate. So this is a circuit, how do you design it? And this is a NOT gate. So we know all the basic gates, or what you call universal gates. Let's look at the other gate. The other gate is Q is equal to A B bar and A bar B. So this is a XOR gate, right? So now how would you design a XOR gate? Let's go this way. Let's equate this to 1. So I'm constructing a pull-up circuit, right? So when I equate this to 1, so what I need, both of these expressions, they are both, right? Both of them, okay, have to be sorry, not both of them. For pull-up, either of them has to be 1. So if it is either case, then one circuit is in parallel with the other. Now we don't know what this is. Okay, now if A dot B bar has to be 1, okay, so either A has to, now in this case both have to be 1, right? A has to be 1 and B bar also has to be 1. So this is a both case. So there are going to be 2 transistors in series. For similarly for AB bar, both have to be 1. So this is going to be 2 in series. And out for the overall expression, either of them has to be 1. So they are going to be in parallel. So this is how I'm going to construct a pull-up circuit. This is VDD. Now if I want to equate this to 0, a pull down circuit, what do I have? Both of them have to be 0. So I have something over here and something over here. Now in this case, for this to be 0, for first expression to be 0, okay, either has to be 0. So it's a either case, means that the switches will be in parallel. Okay, similarly over here, the either case, the switches is going to be parallel. Okay, so now I can represent this in transistor level, in transistor, as there are 2 Pmos devices like this, right? And then there are 2 Pmos devices over here. Okay, so this is Q, and then there are 2 NMOS devices like this. Right? Okay, so this is going to be my pull down circuit. Now my question is, this is VDD. Is there a bar on this? No, there is no bar. So if there is no overall bar, I'm going to invert everything. So for example, this one is AB bar. So I will put here A bar B. And then this was A bar B. So I will put here AB bar. Okay. Similarly over here. Okay. The first term is this one. The first term is this one. So in this case, there is no bar. So I'll put A bar and B. And here for the second term I have A bar B, so I'll put AB bar. So basically you complement the input when there is no overall bar. So this is a XOR gate. Okay, now same thing can be done with the XNOR gate. A dot B plus A bar dot B bar. Now see that this representation, okay, what you see here for XNOR gate is similar in nature here, and there is no bar here, but how would be the connection? Okay, so let's construct a pull-up circuit. Now for this to be 1, okay, either has to be 1, right? So either have to be 1 means right now this circuit diagram is valid. Okay, then for this to be 1, then both have to be 1 here, and this to be 1, both have to be 0 here. So this is a both case, so they are in series. Now let's construct a pull down circuit. In case of pull down circuit, for this to be 0, okay, both have to be 0, so the thing is going to be in series. Then in case of the first expression, for this to be 0, both have to be, so either has to be 0, right? So this will be either case, so they are in parallel now. So this is also valid. Again, A bar B bar, either has to be, so for this to be overall expression to be 0, the either has to be 0. So again it's a either case, so this is there. Now, so the structure remains the same, but what about the inputs? So I'm going to write here, okay, so this is the top structure, what is called a pull up, and this would be the bottom structure, which would be the pull down. Right, so this will be the pull down structure. Okay, now the only difference is the inputs. What will be their first expression? A bar, A dot B, so it will be A bar B bar, because there is no overall bar. Then for A bar B, it will be AB. Similarly over here you have got A bar B bar for the first term and A B for the second term. So this will be a, so you observe that the structure has remained the same, only the inputs got complemented. So this will be a Xor gate. Okay, so these are all the basic gates which I have covered in the static logic, or what you, so static logic family. So we are going to implement this. So I'm going to stop this session over here. In the next session we are going to start with a very basic circuit which is called an inverter. So basically over here, so we'll implement this and we will see, you know, power delay product, and we will see various regions of operation. We will see what is noise margin and stuff like that in the next session. Okay, thanks a lot for this session.